Hi, I'm James Eastham, a developer advocate here at Datadog. In this video, you're going to understand some of the problems that building asynchronous systems brings upon you, and some of the trade-offs, and how getting observability right, is a prerequisite for building asynchronous systems at scale. Now, many of you will be familiar with the idea of synchronous communication. Synchronous communication being you've got some service here. Let's say this is an orders service making a call to another service. Let's say this is the inventory service. Maybe you've got a user here that's making a request to place an order, and at the point the order is received, you want to check that there is actually stock of this order before you try and fulfill it for the user. Now, in this scenario, if you have these multiple services communicating synchronously, at this point, the order service is going to make a call to the inventory service. Remember, the user here is still waiting. The inventory service is hopefully going to do some work. It's going to do some processing before eventually responding with some kind of response. That might be an error. That might be hopefully a 200. Maybe there's a timeout and it goes back to the user. The complete end-to-end flow here from the user to the inventory service, back again, back to the user, is all completely synchronous. The user is sat around waiting. The order service is sat around waiting, all for this inventory service at the far end. But what happens in this scenario if the inventory service is having some kind of outage? Remember, the inventory service is managed by a team of developers completely independent to you if you are a developer on the order service. This team of developers over here will have their own SLAs, they'll have their own release cycles, their own priorities, their own pressures from their own product managers and their own leadership. That may mean that they ship things very differently to how you ship things on the order service. Maybe they ship a new feature out, and for whatever reason, the inventory service goes offline. The inventory service is now not working. In this scenario, if you've prioritized synchronous communication, and honestly, if you're building with synchronous communication and this hasn't happened to you yet, it's going to, believe me. In this scenario, the order service now may also end up having an outage. And of course, if the order service has an outage, that also means your user is unhappy because they can't place orders. Now, of course, I fully acknowledge that there are ways to build synchronous communication between services in a resilient and robust way. But what you're really dealing with here is a problem of coupling. Specifically, you've got runtime and temporal coupling between these two services. At the point the order service is running, at that moment in time, it needs the inventory service to also be running at that moment in time. And this is a particularly challenging form of coupling to deal with, particularly if you're building these large distributed systems where you've got lots and lots of different teams who are all building things independently. It is almost inevitable that one of these services is going to go offline at some time. But of course, when they do go offline, at least it's easy to understand. You can really easily, from an observability perspective, see that the order service is making the call to the inventory service and the inventory service is responding. So although there is these challenges with coupling, understanding cause and effect and understanding the dependencies in your system is a little bit easier. Now, the natural reaction to this challenge of coupling in synchronous communication is to build a more asynchronous system. So what would that look like? Well, we've got our order service and we've got the inventory service over here. Both services are still doing the same jobs, which means you've still got a user making a request into your order service. Instead of the order service sending that synchronous request to the inventory service, the order service is instead going to send a message onto some kind of message channel. So when that request comes in, the message is going to be sent onto the channel here. That message is then going to be routed in some way to the inventory service, which will pick up and then do its work. And maybe if you do need to get a response back to the order service, well, maybe the inventory service sends a message onto its own channel, which the order service is then consuming. This helps you reduce that temporal and runtime coupling. Now, it doesn't matter if the inventory service happens to be offline when a user places an order, because if they do, all that will happen is that the messages will just build up on this message channel before eventually, hopefully, when the inventory service comes back online, it's going to pick up the messages and process them. But what is a message, I hear you ask? What is one of these little things that are being sent between systems? A message is simply just a packet of data. If you make a HTTP call to another service, you are sending a message. Here, we are just sending a message over some kind of message channel. And whilst this does solve some of the challenges with coupling, it does increase complexity in what I would call the day two stuff. The stuff that you need to worry about as a developer once this system is running in production. Not least, understanding cause and effect. Understanding that actually, yes, the order service is having an impact on the inventory service, actually it becomes really difficult to understand that that challenge is happening because there is no direct communication. Because you've got this message channel in the middle, it makes it kind of difficult to understand cause and effect. And when you've got these large-scale distributed systems where all these services are communicating with each other and working together to get work done, cause and effect is kind of an important thing. So these messages that I've just talked about, there's a few different subtypes of messages. You've got commands, you've got events, and you've got queries. These are the three subtypes of messages, if you will, these things that are going to be passed between systems. Now, the difference between commands and event is mostly just a statement of intent. With a command, one system is telling another system, hey, I want you to check the stock for this order. I want you to place this order. I want you to take this payment. Whereas an event, a system simply publishes the message, and maybe there are some systems downstream that are going to consume and be interested in that message. Order created, payment cancelled, stock reserved. These are all examples of events that systems just emit, and maybe there are downstream consumers, maybe there aren't. And then you've got queries, which are more about retrieving some data from a database and returning that to a user. So queries, we can kind of forget about for the moment. What we're interested in now is commands and events. Now, mostly if you're doing synchronous communication between services, one service is calling another service, you're either using a query or a command, because you've got one service that is telling a service that it knows about what to do. That is an example of a more point-to-point style of communication. You've got one point in the system, one service, making a call to another point in the system, another service. And point-to-point communication is one such way of doing asynchronous communication as well. If you're using point-to-point communication in your asynchronous system, you've got one service that is sending typically a command onto some kind of message transport, and there is going to be exactly one consumer. Which service is going to consume that message? You're just using an asynchronous message channel by way of adding that element of durability, of reducing that coupling. In most cases, if you're doing some kind of point-to-point messaging, you've got one producer, one consumer that are communicating asynchronously. Most of the time here, you're going to be using some kind of queue. A queue is just a durable piece of infrastructure that holds these messages durably until the point in which some kind of consumer comes along and picks them up. Now, the other way of transporting message around is what's known as pub/sub or publish-subscribe. In publish-subscribe message channels, you've got one producer still producing the message onto some kind of message channel, but you may have n number of consumers. There is no real way of telling how many downstream consumers you have. And when you publish this message as a producer, this same message is then delivered to all three consumers who all get their own copy of that message to then go off and process. Now, with both of these scenarios, it is still really tricky to understand cause and effect, because although in this scenario, you know that this service is kind of communicating directly with this service because you've got this point-to-point integration, there's still no real way to see that directly. And equally in publish-subscribe, it gets incredibly difficult to understand cause and effect because you, as a producer, simply publish this message onto the message channel, but you have no way to understand, are there 3 consumers? Are there 1 consumers? Are there 100 consumers? Now I need to make a change to this message and I've got no idea who is downstream of me, who is depending on this message. And equally, as a consumer in an asynchronous system that's using publish-subscribe, how do you understand who are you dependent on? How do you understand who is upstream of you and publish that messaging? So you've successfully reduced the runtime and temporal coupling. Fantastic. Good job. But you've also made things a little bit trickier to understand, a little bit trickier to debug. When your page goes off at 3 o'clock in the morning, frankly, you don't want to be picking around trying to work out at that point where exactly the problems are. Now, the simplest way to think about observability in this scenario is to think about what I would call the unit of work. So imagine you're a developer on the orders service. And inside the orders service, there are a few different subsystems. You've got the API that's receiving the request from the user, and then you've got a few background services that are doing other pieces of work inside the context of processing an order. And then you've also got the inventory service over here. The inventory service also exposes some kind of API, and the inventory service also has its own set of subservices or subsystems. As a developer on the orders service, you care about this set of things here. And as a developer on the inventory service, you care about this set of stuff here. As a developer on the orders service, I don't care about what goes on inside here. All I care about is this dependency between the two systems. So when you think about observability inside asynchronous systems, what you should really focus on as a developer is the unit of work. What is the unit of stuff that you care about directly. So you should care, absolutely, that the inventory service exists, but you don't necessarily care about all these internal implementation details. And this is what you're going to learn a lot more about throughout the rest of this video series. In the next few videos, you're going to learn about distributed tracing, about trace propagation, about some of the challenges with trace propagation and how you might use span linking, evolving asynchronous systems, what metrics you should care about. There are a whole bunch of things we are going to cover in this video series. So today, we just set up the problem. In the next video, we'll start to look at solutions. And if you don't want to miss that video, make sure you head down underneath the video, hit that subscribe button, and you can make sure you see the next video in this series when it appears on your channel. And with that, I'll see you all in the next